Okay, let's get started with today's stuff. So, quick recap on the last two types of topological spaces we've been talking about. We've been talking about once you have topological spaces established, how can we create new ones from our existing ones? That way we don't have to rethink them up from scratch. We can use existing intuition, stuff like that. We talked about topological subspace. So you have your topological space, you look at a subset in that topological space, and then you make the open sets, just the intersection of the open sets in the big set with the subset that you're talking about. That gave you your open sets. Remember topological subspace? And then you had your product topology, which is when you have two sets, A and B, then we want to take their cross product, so we want to take the cross product of A and B and endow it with the topology, knowing the topology on this and this. And what did we do? We said intersect all the basis elements in this thing with the basis elements in this thing. That gives you your basis elements for this thing. So if your basis element in here was an open interval like that, and your basis element in here was an open interval like that, and your basis elements in here are these little open rectangles. Right? Mm-hmm. So now, the type of topological space we're going to talk about, the last one, is called a quotient space. And so, let me give you some intuition for how this quotient space thing works. So imagine, remember I, what's I? I is the closed interval 0 to 1.
That's it. Yeah.
Oh yeah.
Right? So I cross I is a unit square, right?
Yes.
Okay.
You with me?
Yeah.
Let me, good, piece of paper. Let me try and help make this make sense with this piece of paper. So imagine I have I cross I here. Now with a quotient space, one of the things we don't necessarily have to do, but one of the things we do a lot of the times with quotient space, one of the ways that they're really useful, is we start identifying points with each other. So imagine first of all, I took the point here. We'll come back to what this means later, but I'll talk about high level for now. Imagine I glued all the points here with the opposite point over here. So I glued this point to this point, this point to this point, this point to this point, this point to this point. So that's taking this paper, and I take all the points here and identify them with all the points here. And what does that give me? Remember what this topological space is called?
Cylinder.
Not a cylinder. It's the one annulus, right?
Yeah.
Because you could take it like this, and then you could flatten it out into just like that, where we're talking about these points. Remember,
So you're talking about points inside or just around?
on that surface, right there, around. So not that, not this, just here. Let me try it one more time. The annulus is these points. Right? So imagine I put this paper like that, and imagine that all this stuff was rubbery now, so I could kind of stretch out the edges and flatten it into a disc shape. It'd look like this, right? That's the annulus. Remember, the cylinder is reserved for when we do I cross R. So if this goes on for infinity, then we call it the cylinder. If it doesn't go on to infinity, we call it the annulus because it can be flattened out like this. So far, and the way I typically write what I just said, I'm going to identify this side with this side. That gives us this. Now imagine that I also went along and identified this side with this side. So that's taking the points from here around and connecting them on this side over here. And that's going to give me a donut, or the torus. Remember, it's just the
I
surface.
knew what that was.
We're talking about just the surface, not the solid thing. Okay? So, when it's all said and done, this is going to be a quotient topological space of this. Okay?
Okay.
And the way that we did that is we identified points with each other. We said this point, we're going to call this point and this point really the same point. We're going to call this point and this point really the same point. We're going to call this point and this point really the same point, etc. But this point was still just identified with itself. We only did that on the edges. You with me?
Okay.
Yeah.
That's very high level what we're going to create here. Now, for those of you from discrete math, there's another concept that it's going to be useful if we're comfortable with it. and that is partitions or equivalence classes. You remember those?
Yeah.
Partitions / equivalence classes?
Yeah.
Okay, so what do we do there? We take the entire, you know what it means to take a partition of a set, right?
Yeah.
Just part of it.
A partition, I'm going to divide all the elements of my set up into sets. So now I have sets of sets. So a useful one to always think about is time. So imagine that right now it's New Year's, midnight New Year's Day, right? And we're going to think about just the hour hand on a clock. And what I'm going to do, so here's time starting at 0. So here's New Year's. We drop the ball, New Year's, everyone's cheering. And now time's going to go forward, and I'm marking out hour increments. You with me so far?
Mm-hmm.
Now I'm going to map each time to whatever the hour hand is pointing to on a clock. You with me?
Yeah.
So from midnight until 1 in the morning, what's the hour hand pointing to?
1.
All the partitions.
Sorry, 12.
12!
What?
Here's 12, here's 1. Hour hand's pointing like that as the minute hand goes around, right? And the hour hand starts at 12 and slowly gets closer and closer to 1
Yeah.
until it's 1 in the morning an hour later, right?
Okay.
So maybe instead of thinking about that, think about a digital clock, the hour on a digital clock. Ignore AM and PM. A digital clock, it would say 12:00, 12:01, 12:02, 12:03. We're just caring about what the hour hand says.
Okay.
So from midnight until 1 in the morning, the hour hand just says
12.
12. So we're going to assign all the points from 0 to 1 to the number 12.
Yeah.
And now from 1 until 2, we're going to assign it to
1.
1. And these ones we assign to 2. And these ones we assign to 3, etc., etc., etc. Notice what happens once I get to right after lunch the next day, I'm back to 12, right?
Mm-hmm.
And it's going to cycle and cycle, and I'm going to assign to 12 again, 12 again, 12 again, I'm going to assign to 1 again, 1 again, 1 again. And we could have also gone back in time. I could have said if I was assigning these ones to 12, then the ones over here I would have assigned to 11 of the previous year, right? So if we think about time as this real number line, notice I just assigned every instant in time to a particular number here. You see that mapping?
Yeah.
So that type of mapping is what we're often going to be doing again with these quotient topologies. I just want to bring a more complicated example that hopefully is already familiar to you because of time before we continue. This was in the book.
Okay.
But this all makes sense?
Yeah.
Yeah.
Anything weird happening there? You see how the entire real number line has been mapped to just 12 points, 12 numbers. Make sense? Okay, so now with a little bit of intuition in our heads for the type of stuff that we're going to be doing here, let's get to the actual definition. So let X be a topological space and let A be any set. It could be a subset of X, it could be a completely different set altogether. Here we could have viewed this as a subset of the real numbers, but we didn't have to, right? It happened to be real numbers. We could have just as easily decided that we're going to call this A, B, C, D, E, F, etc. and mapped it to those. So here's our A up here, here's our X down here. So let X be a topological space and let A be any set. Let P be a function from X to A. It maps all of X to A. So let P be a function from X to A, and let it be a surjective or an onto function, or map. You remember what onto means, or surjective means?
Isn't that just from discrete math? Or is that from...
From discrete math, it's from this class, it's from every class that you've ever taken that had functions. Then they talked about either surjective or onto.
It's where everything from X maps to A and everything from A maps to X. Is that what it
No.
is?
So if I just give you that P is a function from X to A, what do you already know? Ignoring all other information.
Oh, you already know that everything X maps to A.
Yes, if P is a function from X to A, we already know that it maps everything in X to something in A.
Now it's saying everything in A maps to something in X.
Is mapped to from something in X.
Yes.
We map things from here to things in here. Right?
Yeah.
Not the other way. This is saying we're mapping from here to here.
Okay, but is it?
The inverse of a function is not necessarily a function.
Okay, wait, what is onto then?
So onto and surjective means that we use up all of A.
Oh, that's what I thought. Okay.
Right, you have the right intuition. So when you were thinking about in your basic algebra class, f of x equals x cubed, we called this one onto. F of x equals x squared, we said this one is not onto. Can you picture these in your head? Is this still too complex?
No, that works.
So Jake understands. The rest of you, you lost what these two things are saying?
No. Yeah.
Not an excuse.
Okay.
Say one's onto and one's
Just
not.
map.
Yeah, let's draw these. What does a cubic look like? Something like this. And it uses up all of y. What does a square function look like? A parabola? It looks like this. It doesn't use the negative values of y. So since it doesn't use all of y, it's not onto. Since this uses all of y, it is onto.
Oh,
Okay.
In your way back when you were first introduced to these things,
Yeah, way back. I'm getting old.
way back when you were introduced to these things, as in you got them in 7th grade, in 8th grade, in 9th grade, in 10th grade, and you got it this year, but this year twice now.
Way back.
In fact, not only have we covered that earlier in this class, we also covered it in discrete math. So that's your 3rd time doing it this year.
Oh shoot.
Oh, bank. Alright. So, anyways, little bit of notation. When I say map, we usually save that word for a function from a set to a set. So a map and a function are the same thing. We just typically call it a map if it's from a set to a set. Right? Function is just a set of ordered pairs that follow some rule. If we have a function from a set to a set, then that's when we usually use the word map. Good with that?
Mm-hmm.
It's just to help us keep straight in our head, oh, it's this particular type of function, the way that we typically use n if we're talking about a natural number and x if we're talking about a real number. It's just convention. You don't have to do it. It just helps you keep track as you're writing out what you're talking about if you keep calling it a map. Make sense what I'm saying? So map's not a special name. It just helps us remember, oh, it's a function like this. Alright, anyways. So let P be a map from X to A, such that it's surjective or onto, whatever you want to call it. Now we're going to define a subset U of A to be open in A, if and only if, you remember this notation?
Inverse.
The pre-image, the inverse of U, or the pre-image of U is another way that we can say that, is open in X. Am I losing you on that one, or should we draw a picture real quick? Here's X. Here's A. Pick some subset of U in A. I pick
Pick some subset U in A.
in A.
Okay.
So pick some subset of A, call it U. With me so far? Now, since X is surjective, it maps to all of A, so it must have mapped points to U.
So take those
So
points.
look at this point, find its pre-image. Oh, that's right here. So if this was Y, oh, here's X. When this was Y, here's X. When this was Y, here's X. Do that for all those points and you end up with this set. We'll call it V.
That's what the pre-image would be.
In this case, V is equal to, if the function from here to here we call P, then V is equal to the pre-image of U. It's all the points that mapped to U.
Oh, that was a -1.
Oh, yeah, sorry. Did I not write that word?
I thought it was like,
Peter news glasses, you can see.
Yeah.
I thought it was like an upside down B on it.
Here comes
No.
this weekend.
P to the -1, an inverse function. Right? So if P goes from here to here, then the inverse goes from here to here.
Right.
P to the -1, that's what we're talking about. Okay. So define a subset U of A, this thing, to be open in A if and only if its pre-image, V, is open in X.
Okay.
You follow that?
Yeah.
So if this thing happened to be open, then this thing's open. If this thing wasn't open, then this thing isn't open. This is open if and only if this is open. That's how we're going to define our topology. The resulting topology on A is called the quotient topology, induced by P, and the function P is called the quotient map. The topological space A is called a quotient space. So just names. So now when I'm looking at this thing,
Definition of a quotient space.
I call A and the topology on A over here the quotient space. I call P the quotient map. And and when I'm looking at X and P, another way that I can call this thing is the topology induced by P.
So is that defining a quotient topology?
Yes. We need to prove that it's a topology, but yeah, that's its definition. We're going to call the sets in here open if and only if their preimage is open here. So I start out with X, tau. I start out with the topological space on X, and I have some function P from X to A. I call things in A open if and only if their preimage is in tau. You see how I'm defining that?
Yeah.
So something is in tau of A, U is in tau on A, U is in the topology on A. If and only if, we look over here, we'll call it X with tau, if and only if V was in tau. What's tau on X? It's a collection of open sets on X.
Yes.
Don't get confused that sometimes we call X a topological space or we call A a topological space. When I call X a topological space, all I'm saying is I'm being lazy and I'm not writing it out like this. This is really a topological space. When I call X a topological space, I'm saying X is a set that has a topology defined on it that I'm not bothering to name right now.
Okay.
Similarly, when I say A is a topological space, I mean A has an associated topology that I'm not bothering to name right now. This is really the topological space. Same way from discrete math, we talk about a sample space. What's a sample space? It's a set together with some structure on the set. That's how spaces work in general. Take a set, give it some associated structure, that gives you space. So don't be confused when I just call A is called a quotient space. We really mean A together with its topology. Good? Feel like you got intuition for what this topology is?
I think so.
Alright, so we only have one proof today, and then the rest is just feel-good intuition stuff. And our only proof is that this is in fact a topology.
Yeah, I was just going to say. Prove that.
Yeah, that's what I was saying. If you were here for definition of topology, you should pretty much be able to keep up with this lecture.
It's been the biggest question I had. Topology has something to do with the closeness of lines, or closeness of points, and they're all combined.
So that is not the way to remember what topology is. I will tell you, so we'll start with, how's a topology useful? A topology gives us a notion of proximity.
Yeah,
That's what it gives us. But never think about it that way, because the actual definition and how it captures that idea are in no way intuitive. So you need to just memorize the definition of a topology, and keep in mind, and there's some way to prove that this somehow maintains proximity, but
that's way in the future.
But my goodness, how much we got to prove to get there is just like 6 lectures worth. I don't know if you were here when we defined the limit.
I was.
Okay, that's proximity.
I know.
Alright, so you start with the definition of topology, and you work your way all the way up to a limit, and then continuity is the other big idea that a topology gives us, which we'll cover next week, which is also very easy, actually. Once you have the definition of a topology, you can give the definition of continuity like that. So that will be a nice break. Anyways, so let's prove that this thing's a topology. What's the properties of a topology? 1.
It includes the empty set and set sum.
Yeah, so if I've got X and I've got some topology tau on X, tau has to satisfy 3 properties. 1, the empty set and this entire set X have to be in tau. Tau is a collection of subsets of X, first of all, right? Because it's a topology. A topology on X is a collection of subsets of X such that these 2 things are in tau. What's the other one?
The intersection of a finite mini set is open.
Perfect. If we take the intersection from I equals 1 to n of open sets in X, then their intersection, so u sub I, where each u sub I is in tau. So if we take the intersection of a bunch of finitely made u sub i's where u sub I is in tau, then the entire intersection is also in tau. And then the last one,
The union of an arbitrary amount of.
the union of an arbitrary collection of open sets is also in tau.
Yeah.
So take any subset of tau you want, union them all up, that's also in tau. So here we can only do finitely many, here we can do an arbitrary amount.
Okay. I forgot I've ever laughed. This definition is just funky. It's just is very much like a cat is a cat.
Okay, quiet.
What I'm saying is literally of course.
Literally, of course. No. None of these properties are in any way obvious.
Yeah.
I mean, you might say this one.
No, I'm not saying obvious to think of. I'm saying it almost like in. Look at what you're saying.
It defines itself.
No, it makes sense why it's talking about proximity.
Alright, well, if that makes sense to you, wonderful.
Okay.
Because how that gives you a notion of a limit,
It'll give you a notion of the limit.
that's how you get proximity.
It looks like it's just saying this thing is closed and contained. Everything
No,
that's
That's
everything
not
that
what
you
it's
can count.
Look. Let's put the empty set in here. We'll put the set A in here. We'll put the set A, B, C in here. So this is on the set A, B, C. And let's do another one.
This is your X. That first one's your X.
This is X. X is equal to A, B, C.
Okay.
Alright?
Now,
So look at this set. Now look at this set.
is this your tau?
Forget the towels for a second. Just rather than writing that out, I'm just going to put X. Okay, I want to add stuff on. Look at these two sets. These are both sets of subsets of X, right? Now this one is a topology and this one isn't.
Because the intersection.
Because the union of these two sets isn't in there.
Oh yeah. Union
So these
doesn't-
are properties that the collection of sets has. We have to have, the empty set has to be in there. The entire set has to be in there. For any set you have in there, their union has to be in there. And for any finite number of sets you have in there, their intersection has to be in there. Any, when we're talking about union, but only finitely many when we're talking about intersection.
How do those intersect to form X? On what? On the tau.
On this one, pick any number of sets you want in here. Let's take these two. Is there union in here? Yep. Is there intersection in here? Yep. I can pick any sets in here I want, intersect them. I'll get a set that's in here. I can take any sets in here, union them. I'll get sets in here. Down here, it is not the case. So this does not work as a topology. This collection of subsets on X is not a topology. This collection of subsets on X is a topology. And so all our rules about topology work when we're talking about this set. They don't work when we're talking about this set. And so why it's okay to talk about proximity on this set and why we struggle with it on this set. I mean, these are very discrete sets, but still. Why topologies are so useful is in no way obvious just from looking at the definition. Because it's like, oh yeah, something like this is useful, but something like this, not so much. Okay? It's one of those things that you just gotta memorize the definition, get comfortable with the definition, and then kind of trick yourself into thinking, oh yeah, I'm starting to see some connections here. But now, it's in no way obvious to me a lot of stuff that results from topology, which is why it's so fun. Talk about such simple things, and you prove things that it seems like you should never be able to prove that with such simple things. Like taking a limit or continuity. Anyways, so we need to prove that this thing is a topology. Alright? Let's name the topology on A. We'll call it tau sub A be the quotient topology on A. Just so we can keep making reference to it and don't have to spell things out too much. Okay, so first thing I need to show is that the empty set's in there. How do I know that the empty set's in there?
The quotient topology?
Yeah. How would I show that the empty set's in there? The only way to show that the empty set is in tau on A is to show that the pre-image of the open set is in tau on X, right?
Yeah.
So, observe that the pre-image of the empty set is equal to what? What's the pre-image of nothing?
Nothing.
Bold. Bold prediction. Yes. Pre-image of nothing is nothing. And nothing is in tau on X. We never named that one, did we? I thought we named it there. Nope, we didn't. You okay with me just saying tau on X without specifically naming it?
Yeah.
So, the empty set is in tau on A. Since the pre-image of the empty set was in the topology defined on X, then the empty set is in the topology defined on A. Good?
Okay.
Pretty straightforward so far?
Yeah. Would you do the same thing for X?
Yeah. Observe that the pre-image of A is equal to
X.
how do you know it's equal to all of X?
Because everything from X maps to something then.
Everything in X maps to something in A, but I could have X be this, I could have A be this, and I could take all of X and map them to just this one point. That's a perfectly valid map.
Yeah.
So,
Okay, so that's all the pre-image. It's all of X.
No, it's
Because all of X goes to A.
Since you've already
all of X goes to A. Yep, there is actually nothing wrong with thinking about it that way.
Well, since
All of X goes to something in A, right?
Yeah.
So yeah, you're exactly right. All of X goes to something in A, so when you take the pre-image of A, you get all of X, even if they do map all to one point. Which is in the topology defined on X. So, A is in tau sub X.
tau sub A, right?
Tau sub A, thank you. Okay, so that shows it for
The first
The
condition.
first condition, yeah. Now you have to show the intersection.
So now we need to show the intersection. So we need to show that if you have finitely many open sets in A, then their pre-image, then their intersection is also open in A. So we need to show that let me come up with a way to say this. So we've got A here and we've got X here.
You need to show that
If I know that V1, V2, V3 are all open in A, I need to show that their intersection is open in A.
That means you have to show those pre-images intersection is open in X.
Yeah, so to show that the intersection of these V's is in the topology on A is equivalent to showing that the intersection of the pre-image of these things is in tau on X. Almost. I need to show that the pre-image of the entire intersection V is in tau on X, right? I need to show the pre-image of this whole set.
Yeah.
So not this, this. You see the difference on those? This is saying the intersection of a bunch of pre-images. This is saying the pre-image of a bunch of intersections.
That sounds like the same thing.
Yeah, that's
Let me write it out more explicitly so you can see what we're saying. We'll just talk about arbitrary function for now. We're not talking about, we don't need to show, well, pre-image, so maybe it will help stick with P. If I want to show that V intersect U is open, I need to show that the pre-image of V intersect U is open. Not that the pre-image of V intersect the pre-image of U is open. I'm not showing this, I need to show this.
Right.
Okay.
Yes.
That's the only weird gotcha maybe in this part of the proof, I think.
Yeah.
So make sense what we're going to do?
Mm-hmm.
So I'm trying to show this is open. Since I know this and this are open, then I know this, right? Where these are open. And then I know this. From this to this is true. In fact, this is equal to this. This is going back to chapter 0 proofs that we did. I think it's like 0.22. I was at the very end of the chapter 0 stuff. I have all the labels on the videos now. So if you went and watched the last chapter 0 video, then we would have done this proof in there. Or at least that's where we would have talked about it.
Okay.
Maybe the previous proofs we did made it so obvious that we didn't actually walk through this. Anyway, so that's ultimately what we're going to use.
Very similar to the other one.
So, start out here, we're going to say, let U1, comma, U2, comma, UN be open in A. Right? Start out with a finite number of open sets in A. We need to show that their intersection is also open in A. 5. Should we name the intersection of all these things? Maybe we'll say this. Then the pre-image of U1, comma, the pre-image of U2, comma, dot, 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 comma, the pre-image of UN are open in X, right? We know all those sets, all their pre-images were open in X then. If U sub 1 was open in A, then its pre-image was open in X. Maybe keep our picture down here for a second. X, A, here's U, here's the pre-image of U. And P maps like this. So if U's open in A, that means that its pre-image was open in X. That's a definition of being open in A. A set's open in A if and only if its pre-image was open in X. By definition of how we set up our topology, right?
Yeah.
Am I overstressing that? Oh, what am I doing? In X. So, then those are open in X, and we know, since there's already a topology on X, then the intersection of those is open in X. By definition of a topology.
Mm-hmm.
Okay, so then the intersection from I equals 1 to N of the pre-image of U sub I then that, which is equal to, then we can now pull out the pre-image of the intersection from I equals 1 to N of U sub I is in the topology on X. And that's what I stressed, lower this a little bit, that's what I was stressing before I wrote this out, is going from this step to this step, right?
Yeah.
Therefore, the intersection from I equals 1 to N of U sub I is in the topology on A. Right?
Yeah.
Follow that?
Yep.
Okay. Now the last one we won't write out as much. But now we need to prove that an arbitrary union of open sets in A is also an open set. An arbitrary union of open sets is open. Last property of the topology. So let U sub alpha be any subset of tau sub A. Right? It is any collection of open sets. This is all open sets in A. This is just some subset of that, so it's just an arbitrary collection of open sets. Notice that this topology could be infinite, so this could be infinite, since it's just an arbitrary subset. So we're not limiting ourselves to a finite number like we did up here.
Okay.
Follow that so far? Okay, so U sub alpha is just an arbitrary collection of open sets. Then the union of U sub alpha, then the pre-image, same thing, of the union, not U, union of U sub alpha the union of the pre-image of the U sub alpha. There we go. So since I know that U sub alpha is open, then I know the pre-image of U sub alpha is open, right, in X. Since this is open in A, then its pre-image is open in X, right?
Yeah.
So the union of a bunch of open sets in X is still open in X. So the union of those, which is the same thing as the pre-image of the unions, of U sub alpha is in the topology on X, which gives me that the union of U sub alphas is in the topology on A. And we're done. Follow that?
Yeah.
Anything weird?
Makes sense.
Okay. So the quotient topology indeed gives us a topology. Now we're just going to deal with a bunch of examples. So first one, let R with the standard topology. You remember the standard topology on R?
Yeah.
What are open sets?
Open interval.
Open intervals and unions of open intervals, right? So we have R with the standard topology, so R is going to be our X in everything we've been writing over here. And now let's come up with our quotient map. Our quotient map is going to map all of R to just the points A, B, C. And here's how we're going to do it. For any X, if X is less than 0, we're going to map it to A. So we're going to map all the negative numbers to just A. We're going to map 0 to B, and then we're going to map all the positive numbers to C.
Okay.
You understand what the map's doing?
Yeah.
I think so.
It's kind of like what we did over here, mapping all the real numbers to just 12 points. Here we're mapping all the real numbers to just 3 points. But this mapping is a lot simpler, right? Okay, so now, what is the topology induced by P? In other words, what's the topology we now have on the set ABC? What's the topology that function gives us?
The whole row of numbers.
No, we're talking about the topology now on ABC. We're talking about a collection of subsets of ABC, a topology on ABC.
The empty set.
Would it just be
The empty set's in there, bold. The empty set's always in there.
Only the empty set.
the real numbers?
The real numbers,
No.
No, ABC. would be
ABC.
in
The
there.
same.
ABC would be in here.
Okay, wait, what are like? Wouldn't A, the set of A be in there?
A would be in here. The set containing A would be in
And
here.
then the set containing B would be in
And
there.
the set containing B. Wonderful.
Oh,
And then
of
the
course.
set containing
except for not B, just C. Alright, let's make sense out of each of these. First off, the empty set's in there, a duh, right?
Yeah.
The entire set's in there, a duh,
Yeah.
right? And I'm missing one.
B.
No, AC.
AC. Yeah.
C, A, C, squiggly, squiggly. Okay, so remember, a set is open here if and only if its pre-image is open in R. What's the pre-image of the empty set?
You cannot have an open image with just 0 on R, or an open set on R with just 0. That's why you didn't.
Correct.
Okay.
But let's go through it one at a time now. What's the pre-image of the empty set?
The empty set.
The empty set. Is the empty set open
Yes.
in R? Yes. So this is now open in our new topology. What's the pre-image of ABC?
All R.
All real numbers. Is all real numbers open in the stereo topology of all real numbers?
Yes.
Okay, so ABC's in there. What's the pre-image of A?
All
Numbers.
Negative.
All negative numbers. All the numbers from negative infinity to 0. Is that an open interval or union of open intervals?
Yes.
Yeah.
Yep. So this is open in the stereo topology on R. Therefore, A is open in our topology. What is the pre-image of B?
0.
0.
It's
The set containing 0, right?
yeah. And it doesn't have an open.
Is that set open in on the real numbers? Is this an open interval or a union of open intervals?
No.
No. What's an obvious reason that that can't be expressed as a union of open intervals?
Because you can't get closer to the edges.
How many elements are in every open interval?
Infinite.
Infinite.
How many are in that?
One.
Can I union up infinities to get 1?
No.
That'd be quite the trick.
I could probably do it.
Okay, so B is not, the set containing B is not an open set. Let's look at the set containing C. What's its pre-image?
Oh, yeah.
0 to infinity. Is that an open interval or union of open intervals?
Yes.
So its pre-image, so its image, C, is open. Since C's pre-image was open, sorry, I'm being lazy with my words. Since the pre-image of the set containing C was an open set, then the set containing C is open. Right? Now, what is the pre-image of the set containing AC?
Interval of 0 to negative or negative to 0 union with the interval 0 to infinity.
Exactly. Is that an open interval or union of open intervals?
Yep.
Yeah.
So it's open in the real numbers. So the set containing AC is open because its pre-image was open. It's that simple. You're wondering, is the set open? Just look at its pre-image. If its pre-image is open, then the set's open under the quotient map. Good? Ready for the next example? That example probably helped a lot, huh?
Yep.
Probably should have done a couple examples and come back and did the proof. Oh well. Let's look at the next one. Alright, so once again, let R with the standard topology, and let P be a function from all the real numbers to Z. What's Z?
Integers.
The integers, wonderful. And here's how we're going to do it. We're going to map a number. We're going to map it to itself if we happen to choose an open integer, or if we happen to choose an even integer. So if x is an even integer, then we just map it to itself.
Okay.
And then, otherwise, we map it to n, where n is the integer that's not even containing that. N odd. This sounds messy, but once you see the picture, you'll pick it up pretty easily. So here's how it works. So we take the point 2, and that maps just to, or negative 2, and that just maps to negative 2. Right? Now for all these points, we map all these now to negative 1. So for all the points x, if x isn't an even integer, then you map it to the open interval that contains it
All the
around an odd integer.
So all the real numbers do map to that.
So pick any x you want. I'm going to pick a random x. Here's a random x, right? What does it give me? What does it spit out when I plug that one into the function? It spits out
3.
3. Wonderful.
Yeah.
All the numbers within the interval surrounding 3 spit out 3. And then 2 spits out 2. So that -2 goes to there. All those points go to -1. 0 goes to 0. All these points go to 1. 2 goes to 2. All these points go to 3. And I think you see how it works, right? Okay. So we're going to look at just some random sets and see if they're open or closed, just to try and get a feel for this. 5. Is 5 open?
No.
What is the pre-image of 5?
Oh, 6.
No, it's
the
everything
open
in between
interval
6
from-
and 8. Or, sorry, 4 and 6.
Yes, it's open.
It's open. That's
The
no.
pre-image of 5 is the pre-image of the set containing 5, let's be completely correct here, is equal to the open interval from -4, or not -4, from 4 to 6.
To 6. Which is open.
Is this interval open in the standard topology on the real numbers?
Yes.
Yep. Then that set is open on our induced topology.
Yes.
So the set containing 5 is open. Now remember, just because a set's open doesn't necessarily mean it's not closed. A set can be both. So let's also check to see now if it's closed. Is the set containing 5 closed?
No.
No. Its pre-image, the open interval 4 to 6, is not closed on the set of real numbers with the standard topology. What do closed sets look like in the standard topology?
The brackets.
It includes
Closed intervals.
Yeah.
They look like those things.
Yeah.
Not open intervals. The closed sets are closed intervals. The open sets are open intervals. Right?
Yeah.
Okay, so this set is open and not closed. And 4 should be the exact same thing, right?
No.
No, let's look at 4.
Just one integer.
The pre-image of 4 is what?
4.
The set containing 4. Is the set containing 4 open?
No.
No, so it's not open. Is it closed?
No.
Yes, it is.
No.
Contains itself.
Well, that doesn't matter.
No, it isn't.
A set is closed. How do we check if a set is closed?
You can't find infinite points in it.
A set is closed
Oh, if
if,
it's complement, if
you know,
its complement is open.
if its complement is open. What's the complement of the set 4?
Oh.
Negative infinity to 4, not using 4, union,
Right.
4 to infinity. Is this open?
Yes.
Then the set containing 4 is closed. So it is closed. Alright,
Oh, geez.
let's look at 3, 4, 5. Is that set open?
No.
Yes. It's a set of
don't
set.
think you can.
It's a
Because
union of
4
all
is-
sets.
What is the pre-image of that set?
3, 4, 5.
Oh, it'd just be the open interval of 3 to 5.
Almost.
Open interval of 2 to 5. 2 to
Almost.
6.
There you go.
2 to 6. Yeah.
2 to 6. The pre-image of the set 3, 4, 5 is equal to the open interval from 2 to 6.
Because it includes
The
4.
pre-image of 3 gives us all these points.
Yeah.
The pre-image of 4 gives us this point. The pre-image of 5 gives us all these points.
Oh.
So we just barely got all those points from
Yeah.
2 to 6. You follow that? Okay. So now, is it closed?
The next one?
No, 3, 4, 5. Just because it's open doesn't mean it can't be closed.
No.
Yeah.
Open or closed?
Open.
And?
Close.
There you go.
To the door.
There you go. Remember the joke.
Open.
Okay. So that one was open and not closed, right? Now let's look at the last one. 4, 5, 6. What's its pre-image?
5.
It's a closed interval of.
Oh, 4, 5, 6.
It's the closed interval from 4 to 6. Do we see that?
Yeah.
Well, that's cool.
So it's a closed set, and a closed interval is not a union of open intervals, so it's closed, not open. Okay, so there was another example. Kind of a weird topology, but I think it's helping your intuition still, right? Okay, so now remember that we said that the A that we're creating our new space on can be any set, doesn't have to be a subset. There's a particular type of A that we're very interested in, and it's when we create a partition on X. So we start out with X, and we create a partition on X, and then we create our new, we're going to create a quotient map from X to the partition that we created on X. And those are going to be the types of quotient spaces we use the most. And that's exactly what we did up there when we created the torus. We took every point in there, and we created a partition with the point. So, for all the points in here, the partition I created was the set just containing that point. So I went from X to over here, I went to the set containing just X, right? That's what I did for all the points in here. When I got to the boundary points, when I had a point here, call it A, and I had a point here, call it B, I put those together in the same set, A, B. So I said I'm going to call these points the same point in my new topology, and I'm going to call this point the same point in my new topology. And I took this one and this one, call it C and D, and I decided I'm going to put those together over here as just a point CD. So that's often how we're going to create these types of topological spaces, and you see that we're going to do this thing, this gluing thing a lot. So let's get comfortable with what exactly I was saying down here now. So let X be a topological space, and let X star be a partition on X. What are the elements in X star?
Parts in a partition.
Yeah, but tell me the things inside of there. What do we know about the things inside of there? No. Imagine there's some little.
Infinite of them.
No.
No.
Imagine there's some little kid, and you're trying to tell them about what they already know is in here. So we have subset X, and now we have a partition on X. What do we know about a partition?
It's a topological space.
No. Now you're just randomly throwing stuff out rather than thinking about
It
it.
has to be.
I don't know.
Could I partition the people in this classroom?
Yes.
How could I do that?
Gibson Dudson.
Timson Dudson, right? That's one way I could do it. So I would, instead of having 4 people in the class, I would instead split you into 2 sets where we put all the Timsons in one class and all the Dudsons, or all the Timsons in one set and all the Dudsons in one set. So before I just had a set of 4 students, my partition now is a set of 2 sets, which are both subsets of my initial set of students.
Okay, so there's more than one set in it.
So this is a collection of subsets of X. That's the important point.
So all the characteristics.
And if I union up all the elements in here, what do I get?
X.
X. If I intersect all the elements in here, what do I get?
One element.
The empty set. Because Leah can't show up in 2 different sets. If I partition this class, I can't put Leah in the set Timpsons and Leah in the set Dudsons. She can only go one place. Otherwise, it's not a partition. Does that make sense?
Yeah.
Yeah.
Well, then you change your name. I can't partition a set and put someone in 2 places. One way you can think about is when school starts, you partition the kids into the different classes that they go to. And you can't be in biology and in discrete math. You can only be in one place. And so if I were to take everyone who's in topology and in discrete math and in speech and in English, assuming that those were all classes in the morning, I better get the empty set. Otherwise, we messed up signing up a student and we didn't partition the students. So the union of everything in here gives us back everyone. The intersection of everything in here gives us no one. No one's everywhere. Everyone's only in one place. If I take the intersection of any two elements in here, I get the empty set.
Right.
No student is signed up in two classes, let alone every class. You follow that?
Yeah.
So this is probably the place where you're going to get confused the most when we use these types of maps, is losing track of the fact that this is collections of subsets of this, and not elements of this. And I'll try and make that more concrete with my picture here. I just really want to stress that because I feel like that's the easiest place to get lost. Plus, I lose you guys in discrete math when I talk about equivalence classes.
Yeah.
Yeah, I can tell by the way you're smiling when I say that. Yeah, okay. That's all we're doing with equivalence classes. Same thing. You're just partitioning up some set. Anyways, let X be a topological space and let X star be a partition on X. And let P be a map from X to X star such that P maps each element in X to the collection in X star containing that element.
Okay.
Right?
3.
So if we were thinking about our partition, if we think about this as the classes students are taking, and this is all students, we're going to map each student to the class they're taking, right? Okay. So pretty straightforward. So here's a picture that I'm using to try and help stress this point. So X is all these points from here to here. And we're going to look at some subsets of X. That subset, this is a subset. So that's a set containing one point, not just one point. That and that. So then when I map them, all that comes out are the sets A, B, C, D, and E. And X star is just those sets. So while this might have infinite elements, X star only has 5 elements.
Okay.
These 5 subsets. Does that make sense? Because I think if you got that, then the rest is just going to be all easy from here. Good?
Did we go over it again?
Go over it again.
It's the classroom.
Okay. Well,
Just from the part when I was talking to James.
Well, I don't know when you were talking to James. Okay, let's go over this one more time.
Yeah.
We've got X, so let X be topological space, and we've got this partition, X star, on X. We're going to make our quotient map, P, it's going to map everything in X to something in X star, right?
Okay.
And the map that we're going to use is, let this be a map such that P maps each element in X to the collection in X star containing that element. So the analogy I used is, let's say that X is all the students in the school and X star is the students in the class, right? So then P maps you into the class that you take. That's all it does. So for Tuesday afternoon, it maps you to, if this is only for Tuesday afternoon, it maps you to the set of all students in discrete math. That's where it maps you. Right?
Okay.
So another way that we can think about it is X over here. Imagine, here's X, and we'll think about these as all the students. Here's all the students taking discrete math, here's all the students taking speech, here's all the students taking biology, here's all the students taking chemistry, whatever. And we split them up into these sets, A, B, C. C here is a set containing one point. It's not one point, it's a set containing one point. With me?
Yes.
C, D, and E, these are all subsets of X. And P just maps all the points in A to A, all the points in B to B, all the points in C to C, all the points in D to D, etc. All right. Make sense?
Yeah.
So if little x is a point in there, then what is P of little x?
A.
All of A.
Yeah.
It maps everything in here to just that point. Follow that? So this is the common quotient map that we're going to use over and over again. The quotient map where we map X to a partition on itself. We can have quotient maps that are other ways, but this is a very useful one that comes up time and time again. And these gluing problems that we were doing is doing this exact thing. Okay, so now let's do, we're going to do one very discrete example. And then we're going to get to gluing problems. Let me move the camera though. Yeah,
It's kind of like
this is the preschool of math, right? Very basic stuff. It used to be a more common thing that, not this, but set theory was taught very early. I'm going to have to move that again too soon. Let me see if I can put it over here and still get that. Okay, that gets everything. Let's actually move it a teeny bit. That other stuff's discrete math, don't worry about it.
Just saying.
Oh, shelf. I have no clue where that came from, but I hate that's in here. Because I hate this desk like this.
Like hiding in the corner.
No, I just hate the space here. And I wish for the love we'd move that bookshelf. Get stuff away from the boards.
You don't like that back scratcher?
No. I can't fit my chair in there, and it hurts me to stand too long. No, we're not to the whiteboard, we're still doing this. Okay. Maybe that will help. That'll do. Okay.
4 inches.
Well, I just need them. Doesn't matter. Okay. Let's do a very discrete example. So let X be the set A, B, C, D, E, and let tau be, we're explicitly writing out topology. Good?
Yes.
Is that for sure topology?
Yes.
I left one mistake in there. So
There's no E.
what's the one set in there that I have to have in order for it to be a topology?
Is it
A,
not
B, D.
C?
A, B, D.
Okay, there's really nothing wrong with it. But now that you're actually thinking about it, we'll continue. Okay, so there's our topology. We're going to let A be the set AB and B be the set CDE. Notice that if we let X equal the set containing A and B, or sorry, not X, X star be the set containing A and B, it's now a partition. Everything in X shows up in either big A or big B. I don't like that these have elements that are the same name. Let me rename these. Let's call them,
What are A and B?
We'll call it U and V. That way, when I just reference them, I don't have to.
Okay, U and V are partitions of X.
Yeah, U and V together give us a partition on X. So,
And that's what X star is.
X star, well, X star is our partition. U we would call a part,
Yeah,
right? That's using
U
proper
is just-
terminology.
but U, the part, contains.
So U is the set containing AB. V is the set containing CDE.
Okay,
So now everything in X shows up in one and only one of those two sets.
yes.
So the set X star equal to the set containing U and V is now a partition.
Right.
Good with that so far? So it's the same type of thing we were talking about over here. Just very discrete now, naming everything, very clear what we're talking about. And I drew a pictorial representation of the topology that we made on X, where the circles give you open sets. So A by itself is open, A union B is open, A union B union C is open, A union B union C union D is open, and then all together they're open.
Yes.
And obviously the one I can't draw is the empty set. Okay? So now we're mapping it over to U and V. Now I already gave you the answers on this one, but make sure that they make sense. Notice that the preimage of U and V taken together is open, right?
Yeah.
And what's the preimage of U? The preimage of U is the set AB, which is open. Now look at the preimage of V, CDE. Is that open?
Yes.
No, CDE is not
Yeah, it's
open.
not
CDE is not in my topology.
Oh, in your topology. Okay, I thought you were saying on X.
On X, CDE is not open.
Because we don't have C.
Well,
It's only open if it's in my topology. The set CDE is not in there.
Oh, okay.
Not a basis, it's not a basis, it's a topology. So you can't union up the elements, right?
Yeah.
Okay. So, U is open by itself, and U and V together are open. V by itself is not open. So our topology, induced by P, is this topology. Here's the topology on X star, given this topology on X, using our quotient, or using our partition mapping.
Okay.
It's the exact same thing we talked about here, just we're explicitly writing out every single element, exactly what everything is. Is there anything weird in that example?
Yeah, that makes sense.
Good? Because that one should be the clearest of them all. If it's not the clearest of them all, I'm explaining something wrong.
No, it makes sense.
Because up there, everything's labeled. Here, you have to put some stuff, figure some stuff out yourself in your head. Good? Okay. Alright, let's get to gluing. So let X be the closed interval 0, 1, which is the same thing as I. And let X star be the singleton set, just X, for all X between 0 and 1. You with me so far? So for all the numbers between 0 and 1, we're just giving it the set containing itself, just singleton set. Along with the set D equal to 0 and 1 paired together. So X star is our partition, and X star is just saying everyone's going to be in their own class except for Lee and Peter, you two are in the same class. That's kind of what we did.
Okay.
Everyone gets their own set, except for 0 and 1, you two, you have to stay together. And we're now calling you the same set.
Okay.
With me?
Mm-hmm.
Okay. So we think of the quotient topology on X star as 0, 1, as this interval, 0, 1, with the endpoints glued together. We just identified 0 with 1. Everything else was just paired with itself, but 0 and 1 now got paired together, which gave us a circle.
That's cool.
So this point was now D, and this point was D. Put them together, and what do you got?
That is cool.
A circle.
Yeah.
So you see now how what we were talking about here before makes sense with the quotient map. I use a quotient map to glue things together. And why, when we go from a set to a partition on the set, that gives us the ability to glue.
Yeah.
That is cool.
Alright, so let's do another one now. We're going to look at 3 examples on I cross I. What's I cross I? It's just a unit square.
Yeah.
So we're going to take the unit square and we're going to keep creating partitions on it. I'm not going to explicitly write out what the whole partition is. I think you'll get it from here on out. But we're going to write out some interesting ones. So I'm going to start out with I cross I. Here it is. And what's the partition I'm going to do? For all the points in the middle, I'm just going to put it in the set containing itself. So this point goes to the set just containing this point. This point goes to the set just containing this point. Now a point here, if it's on one of these two boundaries, not boundaries up here, if the point's here, it just goes to set containing itself. If the point's here, it just goes to set containing itself. Now if the point's here, it goes to a set containing both these points. The point over here at the same height. So I'm just going to pair these 2 points together, these 2 points together, these 2 points together. You with me?
Yeah.
And that's what this arrow means. This arrow and this arrow means I'm going to map these 2 lines together, where I'm at this point to this point, this point to this point. So we start here and we map up going this way. All the way through. That's what that arrow means.
So that's going to look just like your paper.
Yep, you put the paper together, and what do you get?
And
Cylinder.
What do we call it if it doesn't have infinite length?
James said
Annulus.
And I said a dayless.
Annulus, like a washer. A washer for those of you who do construction stuff. Maybe that doesn't make sense.
Oh, I
if
do.
you're thinking about like,
That makes sense.
These washers.
yeah, and nuts. That's washers.
yeah, washers in the shape of an annulus. Okay? Now let's look at another one. Geez, I wonder if I can rip this paper.
You can.
You think so?
It's just the
There's
instructions.
probably some in here.
Just the instructions.
Oh, they just have these papers shoved in there. Okay, weird. Alright, so now I gotta is that gonna work? It's kind of thick. I need to rip like a strip off of this thing. Probably should have done this ahead of time.
I'm thinking
We realized we were in origami.
5 is really weird. It's like a
You can
parachute.
actually do some pretty cool math proofs with origami.
It's like a parachute.
Close enough. Okay, so now in this one, here's what we're going to do. We're going to map the points on this side to the points on this side, but we're going to map the point up here to the point down here. So we're going to twist it as we go. So I'm going to map the points like this, but I've got a twist in the process.
Oh.
And it's going to give me what we call the Mobius Band. So that's called the Mobius Band. And the Mobius Band only has one side. In other words, imagine that you were just a two-dimensional person who lived on this thing. You would only ever notice it having one side. You're right here and you just keep walking, 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 you're back where you started. You were always on the same side. You never went to the other side. You were always on the same side.
So it's not a
So I'm right here and I keep walking.
It's not a ring.
And sorry, I get back where I started, right?
What I
You see how that works?
Yeah.
So we don't have a lot of rigor in giving you intuition with these things. We're just trying to give you some basic intuition with some common topological spaces that come up a lot.
Why do you?
So now, but this kind of gives you a notion of how you could start kind of think about what does it mean for an object to have one or two sides, right?
Right.
Because I never notice if I'm on one side of just this paper, I could never get to the other side without like a hard corner or something. But now, when we rotate it as we go,
Why do you have to twist it?
I have to identify it. Let's see if I can try and find this there. I have it like this, right?
Uh-huh.
But I need to map it so that the point here is mapped to the point up here.
Yeah.
Okay, so I'm going to try and draw a blue dot down and a blue dot up. So those 2 points roughly need to go together, right?
Uh-huh.
Okay, so let me cap this now, and hopefully you can see it. Notice if I just try to touch them, oh, it doesn't work.
Then scoot it down.
If I do it like this, okay, I map those two, but
Oh,
this
oh,
one
yeah.
also needs to go to that one, etc. So I need to map them all together, so if I twist it first and then map it, oh, now they're all going to line up. You see?
Yeah.
And so it forces us to get what we call a Mobius band. Very common shape, Mobius band. You'll notice it's a picture on the cover of the book. Mobius band. Very common object in topology. Mobius strip. Okay. So think you got this one? Understand what's going on here? Every point gets mapped to itself, except the very edges, these two edges. This point still just gets mapped to itself. But now these 2 points get mapped to the same point, and these 2 points get mapped to the same point, and these two, and these two, and these two, etc. With me? Okay. Now I want you to just, don't say it when you see it, but just kind of stare at this and see if you can see what this one is.
It's the TARDIS, isn't it? Or the...
What did I just say? Don't say it out loud if you see it.
Sorry.
I saw a sphere. That's all I
It's a
saw.
donut.
But here's what we're doing.
Looks delicious.
We're pairing these sides together, and all 4 of these corner points are the exact same point.
Oh, I didn't see that.
Oh, that's cool.
And now we all know what it is, right?
Where is it? The donut?
Yeah, it's the donut. So I can't quite do it for obvious reasons, but we can get a good feel for it. I need to identify this side with this side. That's just giving us the annulus,
Do it.
or a finite cylinder. Jake thinks he can pull it off. He doesn't know what he's trying.
Hold those
Mark.
3 corners.
And now I need to attach this. Notice now my point C. I have one C right here on this end and another C right here on this end.
And they're the same.
So now I need to make those the same point. I need to make all the points on the top the same point, so then I got to bring it around and hook it on itself, which gives us a torus. Okay, so now let's really mess with your brain, and let's look at this one. This one is called the Klein Bottle. Now here's how this one works. I associate this side with this side just like we did before. But now,
You gotta twist it.
when I associate this end with this end, I have to rotate it in the process.
You
Rotate
can
it
do
or
that.
twist it. Same thing.
Twist it, rotate it. The same way with the Mobius band. I couldn't bring it around like that. I had to rotate it first and then bring it around. For the Klein bottle, I've got something like this, and then I need to bring the top around and attach it here where I twist it first. This object you cannot create in 3-dimensional spaces. You need 4 dimensions of space to show what this object looks like without making it intersect itself.
Are you serious?
I am very serious. It's called the Klein bottle. It's a fascinating, you can buy 3D things of this, so let me give you a picture of what it looks like. There's no chance of me drawing this out and having you know what I'm talking about. But here's what it looks like. I don't know if you can see that picture. For people on the camera, they can just Google it and get way better pictures, so I just won't worry about the camera. So you start with this, identify those 2 edges, gives you the cylinder, right? Now, okay. Now he's getting ready to identify the bottom and the top with the cylinder, so he's stretching it out, right? But now he's got to make the rotation. He can't just hook it on. He needs it to be oriented the same way that you've got to go through the surface, basically, and plug into it that way. If you bring it around, you create the torus, and you identify them the same way. You've got to hook it inside, basically, to make it work. Now, there are so many cool videos that you could go on YouTube, and you could Google, like, constructing the Klein bottle, or just the Klein bottle, and you'll see these cool 3-dimensional reshaping things of it coming together, and there's tons of cool ways to see it. So, seeing a picture of it isn't near as great as actually
But in 3-dimensional, does intersect.
in 3-dimensional space. If you tried to do a 3-dimensional Klein bottle, if you tried to do a Klein bottle in 3-dimensional space, you can't fit it. And this is actually kind of fascinating because the Klein bottle is just a surface. If you lived on the surface of a Klein bottle, your world's a 2-dimensional world. So it's a 2-dimensional world that you can't even project in a 3-dimensional universe.
That is so
You need a 4-dimensional universe to project the Klein bottle without making it intersect on itself. The same way that you couldn't project a Mobius band into 2 dimensions.
true.
You need 3 dimensions to project a Mobius band.
But it,
Similarly, the closest relative of the Klein bottle is a Mobius band. Because another way you can think about the Klein bottle is you start out with the Mobius band. After I associate this edge with this edge, then I need to associate this edge with this edge. The exact way you want it. So after I make my Mobius band, just take this edge and bring it around and connect it with this edge and you're done. So we start with that. Now I need to associate my rough edge with my smooth edge. And if I connect those, then I now have my Klein bottle.
What's the use of the Klein bottle?
What's the use of it?
Yeah.
I mean, if you're talking about like actually going and purchasing a Klein bottle, it just looks cool. But it's a mathematical object that comes up a lot in topology.
How do you get water in and out of it?
Yes, so the same way that this only has one side, the Klein bottle has no inside. So
If
you
put-
couldn't store liquid inside of a Klein bottle.
Well, if you put the liquid in before you made it and tipped it upside down, the water wouldn't come out because it would just go up to the same point as the bottle because it all circles.
The outside and the inside are the same side. There isn't inside and outside a Klein bottle. There is in 3 dimensions,
in 3 dimensions.
but in 4 dimensions there isn't an inside and an outside. If you existed on the surface, you could do the same thing where you start here and you just keep going around, and you get back where you started. Because this is like a piece of a surface of the Klein bottle, right? Kind of like the same way that you can think about this as a piece of a surface of a cylinder. Well, not quite, because that is a cylinder. I don't know. Hard to get good intuition for it, but I strongly, strongly recommend you just go and watch some videos of a Klein bottle like being formed, just with some computer graphics generating it. That'll give you far better intuition than just me talking for even 20 hours about it. It's just one of those things as you see it, things start to click. So I definitely go look at Klein Bottle. Just go look at pictures of it. Go listen to people just show you cool things about. Absolutely fascinating. Okay, next one. The sphere. Here's how you get a sphere from a disk. I start out with a disk, and then I associate these points with these points. So I've got my flat disk, and I can stretch it out into like a bowl shape, right? That's perfectly fine. And I can keep stretching and bring the top in and close it back in on itself. Gives me a sphere.
That's cool.
You see that one?
Yeah, I think so.
That one's pretty straightforward. And then this one. Here's the other one you want to go look at.
That one's gonna go.
Yep. Exactly that. I'm going to fold it in on itself, but then I need to flip it so that my ends touch the right way. It's called the projective plank.
Gotta check this one.
Yeah.
You're going to want to check this one out, but one useful thing I can tell you about it, I don't have anything sphere-shaped in here. Do I?
Yeah, that globe.
Oh, wonderful. Thank you.
That is cool.
Okay, so the way that you can get this projective plane, the way that we get it is we start out with the sphere, and then we identify every point on the sphere with the exact opposite point. So these 2 points on opposite sides of the world get identified with each other. These 2 points on opposite sides of the world get identified with each other. The North Pole gets identified with the South Pole. Somewhere in Australia gets assigned somewhere in, well, I don't know. Maybe we might hit somewhere like New York.
Yeah, you can see the 2 poles. That is so cool.
So you identify points on opposite sides of a sphere as the same point and bring them together that way.
This one
Feels
is
like
way
they just
cool.
come to one point.
Look, there are different ways of mapping it. Is what this guy.
Oh, there's tons of ways to do it. Tons of ways to do it. So that's one intuition for what this thing is. This is the other one that you can go and you can look up and you can just see tons of cool stuff. People have made tons of cool computer-generated images of the projective plane. Ways to help give you intuition for why we call that thing the projective plane. So the Klein Bottle and the projective plane, those are the 2 big ones that you could easily go dump a couple hours of your life into just watching cool things with it. Okay, don't dump that time in now. Let's keep going and then go back to those things.
I have a question about the surface of it though. Is it all one surface? Or all the same surface like the Klein Bottle? Or is it?
It's similar that the only way we can project it in 3 dimensions is to have it intersect itself.
Well, I'm saying, so there's no inside.
No, there is an inside.
There is an inside on that one.
Okay.
But the outside surface just intersects itself,
Yeah.
I think. Pretty sure. Okay. Connected some. Now, we're not going to be mathematically rigorous here. Again, the whole point of this is just examples of spaces to help give you intuition. We're not doing anything rigorous here. So we can connect 2 random topological spaces together, and we have a way to do that. So if I have some weird topological space here, who knows what it is, and some weird topological space here, what can I do? I can take out an open set here, which would be like an open hole, and I can take out an open set here, which would be like an open hole. You understand what I'm saying? Like, remove that patch from the surface.
Yes.
Yeah.
So imagine that this is like some blown up figure. This is a blown up 8. And I go and I cut a circle out of this one, cut a circle out of this one, shove those 2 circles together, and glue it. That's going from this to this. You see how we did that?
Yeah.
Yes.
I guess.
I don't know why this is so funny, but
Because it's literally so simple.
Simple.
So weird.
Stupid.
it is weird. You say it's stupid, but it's actually pretty cool. It's simple because we're just establishing intuition. We're not doing this with mathematical rigor. We're just showing you, hey, rip out some holes, shove these things together. That's what we mean by S1 hash S2. It's the connected
It's
sum of
gluing
2
the
topological
sides.
spaces.
That's cool.
And you can use this to create other topological spaces. So if I had a torus, I could view the A, obviously, as a torus with a torus. So now I have a way of expressing the shape. Right? You might say, what is that shape? Before we didn't really have a way to say it. I can say it's the connected sum of 2 toruses now. And this one over here, that's a connected sum of 3 toruses. So now, the whole thing together, that's a connected sum of 5 toruses. And that's all it is. So this is the exact same thing, and that's why it's cool, even though you might say it's real simple. You might not have looked at this thing before and said, oh yeah, that's a connected sum of 3 toruses.
Right.
But now you easily can, right?
Yeah.
So, pretty cool. And then another way that we can think about these connected sums, if we want to go back, instead of thinking about the torus as that three-dimensional picture I drew, but instead go back to thinking about it like we did here. So here's the torus, here's the torus. We have 2 toruses together. Rather than counting the number of arrows I drew, I just drew 1 for the same sides that are associated, 2, 3, and 4. You with me?
Yeah.
So, pictorially, we took 2 toruses and we punched a hole in them and we did that. Here's how we did it if you want to use these types of diagrams. So I took these 2. Now I colored in the surface because now we cut out a hole. You with me?
Yeah.
Cut out a hole from each of them. And we're going to associate 5 with 5 now. Notice that the direction changed on those. So the direction changed on those. Now I'm going to expand this one open, and it's just going to be right here. So 2, still 2. 1, 1, 2, 2, 1, 1. I just expand my 5 out. You with me for this one? For this one, I may expand the 5 out, but then I need to rotate it into place. So 3, 3, 4, 4. My 5's still my 5. That 3's that 3. That 4 is that 4. You with me?
Got yourself a little hexagon.
Octagon. So now I associate those 2 sides together, and then this is when Peter came in, so I stopped drawing. So now that side is associated with that side. 2, 2. There's 1. There's 1. That side's associated with that side. 4. That side's associated with this side. 4. And this side, 3, is associated with this side. 3. Now notice that if I asked you, what the heck does that think? What does that think? You would have been, what? But if you look at this now in reverse, and were to cut it, and then view it as those 2 things glued together, then you could have said, oh, it's that thing. So you can do this both ways. Whatever helps you think about it better, this is just for establishing intuition.
Okay.
So we did 2 sections today. The second section is just showing you a bunch of topological spaces. That's what all the whiteboard stuff was, just to help establish intuition for them. So that's everything. Now go to your heart's content, look at Klein Bottles and projective planes, and thank me later.